Hi, my name is Kundan, and today I'm excited to present our work on leader-follower formation swimming in robotic fish that uses pressure sensing to close the feedback loop. My co-authors are Hankun Deng, Micah DeLattre, and Professor Cheng. For this work, we built upon our robotic fish platform that we call the µBot. The µBot is an undulatory modular robotic fish that can steer left or right by adding an offset to its undulating motor commands. Additionally, by using feedback from the overhead camera, the µBot is able to follow any assigned path. To enable the µBot to sense the flow, we added off-the-shelf pressure sensors, one on each side of the µBot's head. And to train the follower µBot to use this pressure data, we used imitation learning. First, we needed to find a good swimming formation. So we let the leader swim at different locations relative to the follower and observe the pressure data, which looks like this at various lateral and longitudinal distances. We observed that in staggered formations, the pressure excitations were larger and the differences between the left and right side pressures were also greater. Therefore, we designed an expert policy that could maintain a staggered formation from the leader by using feedback from the overhead camera. As the leader moved on randomly generated paths, the expert policy gave the needed steering commands to the follower. During this process, we also collected pressure and IMU data in the background. We then trained an LSTM model as the learner policy to imitate the expert policy's actions. However, the learner policy would only use the sensor data and would not rely on the overhead camera. First, we trained the learner with data from the expert policy when it was in control of the follower. Even with increasing number of rollouts, you can see that the follower is still not able to track the leader. Therefore, we started expanding the dataset iteratively by adding the learner's own rollouts to it. We can observe that the follower is increasingly getting better at tracking the leader. Here are some more rollouts from the final learn policy. This is the rollout that you just saw. Here you can see from the blue curve that the learner is able to approximate the expert's steering actions, which is in orange, to some degree. Here is another one, and you can see again that the learner is able to approximate the expert. Here are some more rollouts. And here are some more. Generally, you can see that the follower is able to track the leader. However, there were some rollouts where the follower could not steer away from the leader on time, even though, as you can see here, it was still able to imitate the expert actions to some degree. This was the most common reason for ending the rollout early. In some other rare cases, like this one, the follower lost track of the leader. Starting at around 3 seconds, you can see that the learner is unable to imitate the expert anymore. However, this happened only once in 20 rollouts, and in the rest of the rollouts that were ended early, the follower came in contact with the leader. And even in these rollouts, you can still see that the learner is attempting to follow the leader. In summary, we found that stacker formations have the potential to provide richer hydrodynamic feedback to the follower, and we're able to achieve leader-follower formation swimming using only 2 pressure sensors and 48 minutes of experimental swimming data. So with this, I would like to thank our sponsors, and I would like to thank you for watching. If you'd like more information, please check out our paper and feel free to contact us.